So, hello everybody, welcome to summer school. My name is Peli and I'm a PhD student in the Jürgen Cox's lab. And we will be together for the next almost 3 hours. I'm going to talk about 2 different topics. First is going to be about typical proteomics experiments, and then we're going to talk about some basics of the MaxCon software. So yeah, we thought it's a good idea to start the summer school with something quite basic. So the typical proteomics experiment presentation, because yeah, we want everybody to be at the same level, because after that, during the rest of the day and the rest of the week, we will have more specified presentations. So yeah, I assume, I mean, it depends on your experience with proteomics, but I expect most of the things that I'm going to talk about, a lot of people already know. So yeah, be patient, but I think it's important for the people that they don't know this stuff to put everyone in the same page and then continue after that. So yeah, let's start with the presentation then. Of course, you can ask during the presentation if you have any questions. So yeah. So you came in the summer school, MaxCon summer school, that we advertise it as a summer school on computational mass spectrometry based proteomics. So the least that we can do at least is make sure that everybody understands what kind of summer school they came to. So let's actually detangle these terms one by one. So yeah, let's start with proteomics. So also I want you to be patient with me. The next few slides are going to be full of text and definitions, so which I really usually don't like, but that's what you get when you want to define some terms. So first of all, what is proteomics? So proteomics is the large-scale study of the proteome. But what is the proteome? This is a very abstract definition. So proteome is the whole complement of proteins, including the modifications made to a certain set of proteins produced by the organism. I guess that's also a nice definition. But what is proteins? And that's where I was referring to when I said we're going to go to very basic level during this presentation. So yeah, proteins are biological molecules made up of building blocks called amino acids. So probably you already know. So proteins is like a polypeptide that is like made by a linear chain of amino acids. So here we have an example. You can see probably my laser point. So yeah, you have, this is a peptide. You have the N terminus and the C terminus of the peptide, and then you have the different amino acids. Here, you have 3 different amino acids that you can distinguish based on the side chain, because everything else is the same between the amino acids. So here we have 3 different side chains, so 3 different amino acids. And what happens is that you put amino acids together, there is a reaction that you have condensation of water, so water leaves, and then you create a peptide, a bond between these amino acids that is called peptide bond. So here you can see like the 2 peptide bonds that we have in this example. So for example, here you have the peptide bond between the carboxyl group of the first amino acid and the amino group of the next amino acids. So that's quite basic. And yeah, I gave like a very abstract definition of the proteome here. So of course, like this definition means that when you say proteome, you mean all the proteins of an organism and all the modifications that you can have in these proteins. But for the rest of the week, when we are talking about proteome and when we are discussing about a proteomic experiment, we actually are going to talk about the sum of the proteins that you have in your sample, and that's it. So you have your sample, like whatever is in there that is made of amino acids, then that's what we're going to try to identify and quantify. So don't be confused about this abstract definition of proteome during the week. So I hope that we know about proteomics now. So we are going to do proteomics experiments. We can do proteomics with different techniques, but for this summer school, we're going to show how do you do proteomics using mass spectrometry. So what is mass spectrometry? Mass spectrometry is a sensitive analytical technique used to detect, identify, and quantitate the analytes in a sample based on the mass to charge ratio of the analyte ions in the gas phase. So from this definition, I want you to remember three things that they are very important. So first, when we do mass spectrometry, we measure the mass to charge ratio. So we're unable to measure just the mass itself. So that's quite important. And the other two things that you should remember is that to do a mass spectrometry experiment, you have to have your analytes in gas form. And not only that, but they have to be charged. If they're not charged, then you will not be able to see anything in your mass spectrometer. So yeah, just remember these things. You measure mass to charge ratio, and your analytes have to be in gas form and also charged. So yeah, here you see, I have a picture of a mass spectrometer here. Actually, I put also this thing next to it, which I have the abbreviation of it. It's HPLC, which stands for High Performance Liquid Chromatography. You can actually do mass spectrometry experiments without the HPLC, but this is how we usually do it nowadays. And it gives us way better results. That's why I also put in the picture here. So, but let's locate ourselves a little bit. So you have your sample, and you're going to put your sample in the HPLC first, if you're using HPLC. And then what is going to happen is that, so why we're doing HPLC? So our sample has like a very complex mixture of proteins, of analytes. And if we put all of this complex mixture in the mass spectrometer immediately, then it will not gives us very good results, let's say. So what we can do is that we can make this complex mixture less complex. And that's how we do it by using the high PLC. Yeah, so you put your sample into the liquid chromatography, and then from the column, you elute like peptides at every specific time. This time is called retention time. So yeah, so then from the column, you elute different analytes, and then these analytes go into the mass spectrometer. The mass spectrometer does like its thing. We will see what it does actually. And then it will give us some data, which is in this form. So it will give us mass spectrum, and we will see also what is that. So this is like in a high level of the workflow, but we really care about the mass spectrometer. So actually, let's try and see what it is and what it consists of. So in general, you have to remember that it consists of three different things, mostly. So you have your ion source, which I hope you understand why we need it there. Since I told you that your analytes have to be in charge form, you need something to put charge on your analytes. So this is what the ion source does. So you put your sample in the mass spectrometer. First, it goes through the ion source. Then you have your charged analytes. Then your analytes go to the mass analyzer, where the mass analyzer is responsible to like, how you say, like to discriminate your analytes based on the mass to charge ratio. You can also filter your analytes, but that's a different discussion. But for now, let's focus on that the mass analyzer can discriminate your analytes based on the mass to charge ratio. And then, of course, you have to have a detector to tell you what you actually count at any specific time. So you count how many ions you have at any specific retention time. and the detector is the one that will give you the mass spectra at the end. So you can see here the direction of the ions. So it goes from the ion source to the detector. And also you can see another thing here is that this gray area here, it's high vacuum. So since the mass analyzer is going to discriminate your analytes based on the M/Z, usually it does that by looking at the motion of the ions. So of course, because you want to see the motion of your ions, you want to eliminate as much as possible any like contamination with anything else in the mass analyzer. So that's why we have everything in high vacuum. So yeah, that's the mass spectrometer, more or less. So yeah, let's see again an example of a workflow. So you have your sample, you have your analytes. Here you can see 3 different analytes that you have, the green, the blue, and the red. And then you put it in the mass spectrometer. As we discussed, first is the ion source. So the ion source will make your analyzed in gas phase and also charged. And then the charged analytes will go into the mass analyzer first. And then the detector will give us first the first mass spectrum. We call this mass spectrum MS1, but what it is actually. So first of all, it looks something like that. Let's pretend that it looks like that. But it's actually like for a specific retention time, it's a 2D plot. And as you can see here, the x-axis is the M/Z values, and for the y-axis is the intensity. And the intensity should be proportional to the amount of your analyte. So here you see we have 3 different peaks. So each one of the peaks corresponds to one of your analytes. So it's colored already to be easier to understand. So the green corresponds to the green analyte, and then the red to red, and the blue to the blue. And yeah, since you have more of the green, usually what you expect in your mass spectrum is that the green peak should be higher than the blue and the red. So that's the first spectrum that you get. But that's not enough for you to do an identification and in some cases quantification. So what happens after that? So, wait. Yes. So what you can do, you can actually select one of the analytes to continue your experiment. We will see what does this mean. But let's say that I want the green one to continue with my experiment. So what I will do, first of all, I chose green because it's the most intense peak. And I'm going to isolate the green analytes and remove all the other analytes. And then I'm going to fragment these green analytes. After fragmentation, I will go again to the mass analyzer, and also I will have another MS spectrum that now is called MSMS spectrum or MS2 spectrum. And this is the spectrum that will help us identify the peptide. Again, the axes are the same as the MS1, but now we have the fragments of only the analyte that we chose to do the fragmentation on, so the green one. So yes. So while I was presenting all of this, I actually didn't say the whole truth about this workflow. So I kept some things, and yeah, let's actually go through the things that I didn't actually say. So I was really trying to not say proteins or peptides and just say analytes here. Because first of all, I said that you extract your analytes from your sample. But what these analytes can be? They can be proteins, but also, and what usually happens in most of the experiments nowadays in proteomics, is that you take your proteins and you digest them into peptides, usually by using a protease. For example, usually people use trypsin. So your analytes actually can be either proteins or peptides. If you do proteins, then your experiment is called or classified as a top-down experiment. And if you use peptides, then it's called bottom-up experiment or shotgun experiments. So that's one thing. So let's actually also see it from another perspective. So you have your protein that you start. And then if you immediately take the protein in your mass spectrometer, you're going to do fragmentation on the protein. And this is the top-down proteomics. But what else you can do is you can take the protein, first digest it to peptides, and then put the peptides into the mass spectrometer and fragment the peptides. And this is called bottom-up proteomics. For the rest of the week, we're going to discuss only about bottom-up proteomics. So we put peptides into the mass spectrometer, not proteins. And the peptides is only a means to the identification and quantification of the proteins. So, but it's nice for you to know also that there is also top-down proteomics. Another thing that I didn't say, it's the thing that I showed you only one way to do the experiment, the mass spectrometry proteomics experiment. So I actually told you from your MS1 spectrum, you choose one analyte to continue with the fragmentation. This is not only the only way to do an experiment. So let's actually see the different ways to do it. So you are now in MS1 level. So you have the peaks for each one of your analytes. And then actually here I gave you like the MS1 scan at a specific retention time. So at a specific retention time, the plot it's like a 2D plot. So you have X axis, the M over Z, and the Y axis is the intensity. But for the whole retention time range, what we get from the mass spectrometer is like this landscape that you see here with green. So it's not actually a 2D plot, it's like a 3D plot. As you can see here, again, MS1 level, you have three kinds of information. You have the M over Z, you have the retention time, and you have the intensity. So this 2D plot actually comes if I slice these 3D landscape for a specific retention time. So from the mass spectrometer, we actually get this 3D plot. And for a specific retention time, I have this 2D plot. And what I can do, I can do the fragmentation on a chosen analyte and on a chosen peptide. So for example, I chose the green one here. I will do the fragmentation, and then I will get the MSMS spectrum that corresponds to only the green peptide. Of course, like in another cycle, I can do then the red one and get the MSMS for the red, and then I can do the blue, the fragmentation for the blue, and get the MSMS for the blue. This is called data-dependent acquisition. It says it's called data-dependent because it depends on the data, because what happens is that you will choose to do the fragmentation on the analytes that are usually the most abundant. So that's why it's called data-dependent, but that's the only one way to do the experiment. The other way is that to do data-independent acquisition. So we have exactly the same MS1 3D plot, but now we're not choosing one analyte at a time to do fragmentation, but we are taking ranges of the M over Z axis to do fragmentation on whatever this range consists of. So we're not talking about only one analyte at a time. We're talking about a range, and whatever all the analytes that are in this M over Z range, I'm going to fragment them and try to identify them. So for example, here you see I have 3 different windows of M over Z ranges. Actually, you can have only one big window for the whole range, but you can do different ways of cutting the M over Z axis. But here I have 3 different windows, consecutive windows. And for each one of the windows, I will fragment whatever is in this window, and I will do the MSMS. And as you probably can tell, the MSMS spectra for the DDA and the DIA, they have different properties. And of course, you have to use different algorithms to work on them. Yeah. So these are the 2 different acquisition methods that you can use. So this is a different way to see what I already explained. So now, so before here, you saw this 3D plot, right? The green landscape. Now, let's pretend that we are watching this plot from above. So let's pretend that this red stuff doesn't exist. The green stuff that they're under the red stuff is actually what we saw before, let's say. So now it's the 3D plot in a 2D like view. So you have M over Z, you have the retention time, and the intensity formation comes to in the color of the green color that you see. If it's like very green, then it means that it's very high in intensity. If it's like yellow and or white, it means that the intensity is very low. So it's the same thing that we had here in the 3D, but now we look at an 2D. Yeah, so now let's put the red stuff again on top. So what the red stuff means. So here we are in the data dependent acquisition. So each red like square means that an MSMS event was triggered at that position. Yeah, and for the data independent, you can see that we have the windows again. Another thing that I didn't discuss, there is another kind of acquisition that you can do your experiments that is called targeted. So for that, you have like a list of peptides that you really care about, identify them and quantify them. So you will only try to find these peptides in your data set. Yeah, maybe because you care about, they're very important for disease or whatever you care about. So yeah, 3 different approaches: data-dependent acquisition, data-independent acquisition, and targeted. So for the rest of today, I believe, and the most of the week, we are going to talk about data-dependent acquisition, but also we have some talks about data-independent acquisition. Specifically tomorrow, Jürgen will talk about MaxDIA, which is the algorithm that we have in MaxPand to work on the DIA data. And then on Tuesday as well, we have Christoph that is going to give a presentation on MaxPand Live, which is a way to do targeted, let's say, acquisition, targeted proteomics experiment. So yeah. So yeah, another thing, so now we go to a different thing that I think is quite important for you to understand before we go to the next presentations. It's the peptide isotope patterns in the MS spectrum. So to understand that, let's start with the isotopes and what are the isotopes. So most of the elements in nature, they exist in more than one isotopes. And when I say isotopes, I mean the same element with the same number in different forms. And these different forms will have the same number of protons, but they will have different number of neutrons. So for example, carbon here, it exists in nature in 2 stable isotopes, in carbon-12 and in carbon-13. Both they have the same number of protons, but carbon-12 have 6 neutrons and carbon-13 has 7 neutrons. So of course, since the carbon-13 has 1 neutron more, that will be seen in the mass. So carbon-13 will be heavier than the carbon-12. So you can see it here with a nominal mass. Carbon-12 has 12 Dalton mass, and carbon-13 has 13. Since we're doing mass spectrometry experiments and we're measuring mass, actually mass over charge, you understand that this will affect our measurements. Actually, here you can see also the abundance of the different isotopes. So in nature, for example, for carbon, 99.9% of the carbons existing there in the carbon-12 form. And only 1% of the carbons are in carbon-13 form. So it's quite a very small percentage, but still it affects our measurements because we have like very high resolution instruments. So you will be able to see how it affects our mass spectrum. Yes. So what does this mean? This means that when I say, when I have a peptide, that doesn't mean necessarily one peak in our spectrum. So, but I lied to you when I showed you during the examples that I used, when I showed you the MS1 spectrum, I showed you that for each one of the analytes, I had a peak. So this is not what usually happens. So let's see what actually happens. So let's take another example. Let's say that I have a peptide with X number of carbons. So based on the misinformation that I gave you before, I would expect one peak. And this peak, probably without me knowing about the existing isotopes, I will expect all of my carbons to be carbon-12. But what actually happens? I will have multiple peaks that correspond to the same peptide. So let's say that I have 4 different peaks for this peptide, and we call this isotope pattern, isotope envelope for this peptide. And what are the other peaks? So the first peak is the one with all the carbons being carbon-12. The second peak is going to be all carbons except one are going to be in the carbon-12 form isotope, and only one is going to be in the carbon-13. Then the next peak is going to be all the carbons except 2 are going to be now in carbon-12 form, and then 2 of the carbons are going to be in carbon-13, and so on and so forth. So the thing is that people usually think that this makes like the life of the bioinformatics analysis of the people that they do bioinformatic analysis of the spectra quite hard, because now you have multiple peaks correspond to one peptide, but you can get actually a lot of information out of these isotope patterns. So since we know each peak where it corresponds to, we know what the distance between the consecutive peaks should be. So if we measure the distance between 2 consecutive peaks of an isotope pattern to equal to 1, which is what I expect the mass difference to be, then that means I can get information for the charge. So again, I expect the 2 consecutive peaks in an isotope pattern to be away in mass in almost 1 Dalton. Since I'm measuring in the x-axis not mass, but mass over charge, I can use this information to get the charge of our peptide. So if it's 1, then that means my charge, or the charge of the peptide that I'm measuring is 1. If it's 0.5, then that means that the charge of the peptide is 2. And if it's 0.333, the charge is 3, and so on and so forth. So yeah, I will skip this. Yeah, so now let's go to the questions that we can ask when we're doing a proteomics experiment with mass spectrometry. So first, we can ask what proteins I have in my sample. So I would like to identify the proteins that I have in my sample. That's a very normal question to expect for someone to ask. But then also, I don't want only to know which proteins I have in my sample, but I also want to quantify them. So that's another question. So I want to know the amounts of the proteins in my sample. So the absolute value of these proteins. Then another question is that what are the differences between the samples? So for example, maybe, and usually what happens is that you have a biological question to answer. So you have like multiple conditions, like you have a control and then you stimulate your sample in a way that you want to see the changes. So maybe you want to ask what are the differences between the different conditions. And probably you will say this is exactly the same question as what are the amounts of the various proteins, but this is not quite correct. I mean, if the mass spectrometry was actually very precise and accurate, then if I know the absolute amounts of the proteins in each of the samples, then of course I can take the ratio and like do just like the division of take just the ratio between the conditions. But that's not what is happening. So there are different ways, even in sample preparation, but specifically in the bioinformatics analysis of the algorithms that we are using to answer this question and different algorithms to answer the absolute amount of the proteins. So actually, to find the differences between the samples, it's actually a quite easier question to ask as far as like the algorithms is concerned. But yeah, you will see all of this like later in the week and it will make more sense. And another question that we can ask is that about the modifications of your proteins. So what kind of modifications you have in your sample, and yeah, what amount you also want to quantify like these modifications, and also in which position as well. So I don't know how much time do I have left? I have 10 minutes, perfect. So another thing, yeah, let's see now. So now let's see what kind of experiments I can have that will help me do the quantification. So first we have the label-free approaches. For each one of these quantification methods, we're going to have a specified presentation later in the week. So actually for the label-free, we're going to have a talk today from Christoph. Then we have when you use so for the label-free, you don't have to use any labels. But then we go to the experiments that you need to use labels to do the quantification. And then you can group these experiments in two different groups. When the experiments that you do the quantification in MS1 level, so this is the MS1 label experiments, and the ones that you do the quantification in MS2 level. If you're aware of, but if you're not also, it's okay, because we are going to talk about it later in the week. MS1 level label, for example, it's SILAC, if you are aware of. And MS2 labeling is, for example, the most common one is that people use is the isobaric labeling techniques, for example, TMT, tandem mass tags. So actually for the MS2 labeling techniques, we're going to have two talks, one for theory and one actually like tutorial on Tuesday and on Friday.